You know that feeling when you're on a plane, you're bouncing around like crazy during takeoff, and then all of a sudden you break through the clouds and boom, it's perfectly calm. It feels like you've just entered a totally different world. But why? Why is the air down there so choppy while the air way up here is so smooth? Well, let's get into it because the answer is all about how our atmosphere gets its heat. Right. This is the view we all love. You're cruising at 35,000 feet, the seatbelt sign is off, and the world below is just this beautiful, calm blanket of clouds. It's serene, it's stable, it's kind of boring in the best possible way. But, to get to this peaceful place, you had to fly through all that bumpy, turbulent air near the ground. So, what is the real difference between these two parts of the sky? What changes as we climb that turns all that chaos into calm? Turns out, to figure this out, we need to follow the heat. To solve this whole mystery, we're going to take a trip straight up, right through the invisible layers of our atmosphere. And we're going to see how each layer is heated in a completely different way, and why that single fact is the key to everything. Okay, and here is our map for the journey. We're going to start right at the bottom in the layer we all live in, the troposphere. This is where pretty much all the action happens. So, the troposphere is basically atmosphere's weather engine. And like any engine, it needs a source of power. But its power comes from a process that's probably the exact opposite of what you'd think. It's heated from the ground up. Just think of this layer as our neighborhood. It's where we live, it's where our weather happens, and it's where planes spend their time taking off and landing. But the most important thing to notice here is that temperature trend. As you go higher, the air gets colder. That steady drop in temperature is the signature of the troposphere, and it is the key to all that turbulence. So, how does this actually work? Well, imagine the atmosphere is a giant pot of water on a stove. The sun's energy doesn't really heat the air directly. Instead, it heats the ground. That's our burner. The ground then warms up the layer of air sitting right on top of it. This creates this invisible bubble of warmer, less dense air. Meteorologists call it an air parcel. And because it's warmer and lighter than the air around it, what does it do? It rises. This whole cycle of rising warm air and sinking cool air creates these powerful vertical currents. And when you're in an airplane, you feel those currents as turbulence. But that's not the only way the troposphere moves heat around. There's a second, more sneaky way called latent heat. And it's all about water. It's basically hidden energy that gets stored or released whenever water changes its form. Here's the deal. When ice melts or water evaporates, it has to pull heat energy out of the air around it to make that change happen. So those processes actually cool things down. But the reverse, that's where things get really interesting for our weather engine. See, when water vapor turns back into a liquid droplet to form a cloud, or when water freezes into ice, it releases all that hidden, latent heat back into the atmosphere. So every single time you see a cloud forming, you are literally watching billions of tiny warming events happening all at once, pumping energy into the air and helping to churn that weather engine. Okay, so we get it. The troposphere is unstable because it's heated from the bottom. But our plane keeps climbing. It's time to punch right through that boundary layer, called the tropopause, and enter a completely different world, the stratosphere. And up here, everything flips completely on its head. The rules of the game are totally different, because the stratosphere isn't heated from below, it's heated from above. This quote really says it all, doesn't it? Stable, non-turbulent. This is that smooth ride we've been looking for. But why? Why is it so radically different from the churning mess of the troposphere just a few miles below? The secret ingredient is ozone. Way up in the stratosphere, you've got the ozone layer. It's this band of gas that does us a huge favor by absorbing most of the sun's dangerous UV radiation. And as it soaks up all that energy, it gets hot. This means the heat source is no longer the ground way below us, but this layer of gas way above us. This top-down heating creates something that meteorologists call a temperature inversion, and is the complete opposite of what happens in the troposphere. As you climb up through the stratosphere, the temperature doesn't go down. It actually goes up. And here it is. This is the aha moment. On the left, you have the unstable troposphere, with warm, light air at the bottom that's always trying to rise up through the cooler air above it. That creates constant churn. But on the right, in the stable stratosphere, the warm, light air is already on top. It has nowhere to go, and the cool, dense air below is perfectly happy to stay put. No vertical motion means no turbulence, no weather, just that smooth, stable ride. So we've cracked the case of our smooth flight. But, the atmosphere keeps on going. And things just get weirder the higher you go. Let's take a quick detour and push even higher to see how heating works at the very edge of space. Welcome to the mesosphere and the thermosphere. This is where temperatures swing wildly from the coldest you can find in the entire atmosphere to hotter than you can even imagine. So, above the stratosphere, in the mesosphere, it gets super cold again because there's just no good heat source up there. But then you hit the thermosphere, and the temperature seems to skyrocket to over 1,500 degrees Celsius. Now, here's the weird part. You wouldn't actually feel hot because the air molecules are so incredibly far apart. But each individual molecule is just zinging with an unbelievable amount of energy it's soaked up directly from the sun. Okay, let's bring this all back down to Earth. Back to our airplane. We've seen that stability is all about where the heat is coming from. So how do pilots and meteorologists actually measure and predict this stuff? Well, they use a pretty simple but really powerful concept. It's called the lapse rate. It's just a fancy term for how quickly the temperature changes as you go up. A positive lapse rate means it's getting colder as you climb, and we now know that creates the instability of the troposphere. A negative lapse rate, our temperature inversion, means it's getting warmer, and that's what creates the amazing stability of the stratosphere. And to have a ruler to measure everything against, the aviation world uses a baseline called the International Standard Atmosphere, or ISA. It's just a model that says for every 1,000 feet you climb, the temperature should drop by about 2 degrees Celsius. This is our benchmark, our yardstick for a normal day. And here's the final piece of the puzzle. Stability is really just a comparison game. Remember that rising bubble of air we talked about? If that bubble manages to stay warmer than the air around it as it climbs, it's just like a hot air balloon. It's going to keep rising, and that creates instability and bumps. But if that bubble cools down faster and becomes colder than the air around it, its journey's over. It'll stop rising and sink back down. That's stability. So next time you're on a flight, you'll know exactly what's going on. All those bumps during takeoff, that just means you're flying through the troposphere, being cooked from the bottom like a pot of water on the stove. And that amazing blissful calm at cruising altitude, that means you've made it. You've reached the stable stratosphere, where the heat comes from above. In the end, it all comes down to one simple question. Is the air around you being heated from above or from below? That one thing decides everything.